Please good morning and welcome to our presentation. We are group 19 and we are presenting on the application of electromagnetic theory in the seawater. So these are our group members' names and their corresponding index numbers. So in our presentation we are going to talk about electromagnetic ocean effects, ocean conductivity, motional induction, and then we talk about the governing equations. We will talk about stain depths or the depth of penetration. Then we talk about electric fields of motional induction. We will talk about magnetic fields of motional induction, induction by time varying magnetic fields, ocean induction by magnetic storms. Then finally we talk about the relevancy of the topic under study in our country Ghana, which will be the conclusion. So let's start with electromagnetic ocean effects. So the ocean plays a very vital role in electromagnetic induction due to its relatively high conductivity and the dynamo effect of the ocean currents. So a typical crystalline rock of the Earth's crust has electrical conductivity in the range of 10 to the power minus 6 to 10 to the power minus 2 Siemens per meter. So in comparison, seawater with electrical conductivity within the range of 2.5 to 6 Siemens per meter is a very good conductor. So electrical currents are induced in the ocean by two different effects. One is by induction by time varying external fields, and two is by induction by motion of the seawater through the Earth's main field. So let's talk about ocean conductivity. So while the freshwater has a very low conductivity, a salt concentration of about 35 grams per liter turns the ocean into a very good conductor. So in contrast to the electron and electron hole pair conductivity in solid earth materials, the carriers of charge in the ocean are the hydrated ions of the dissolved salts, and the positive ions are called the anions and the negative ions are called the cations, which is a basic chemistry. And so the conductivity of seawater depends on two things. One, we have the number of dissolved ions per volume, and two is the mobility of the ions, and which is dependent on temperature and pressure. So conductivity increases by the same amount with a salinity increase of about 1 gram per liter and a temperature increase of about 1 degree Celsius. So the change in conductivity is dominated by temperature with a range of about 2.5 Siemens per meter for cold deep water and about 6 Siemens per meter for warm surface water. So motional induction. So when the ions are carried by the ocean flow through the Earth's magnetic field, they are deflected by the electromagnetic Lorentz force. And the direction of the Lorentz force on the anions is given by the right hand rule, which is the thumb finger pointing in the direction of the ocean flow and the index finger in the direction of the magnetic flow. Then the middle finger indicates the direction of the deflection of the anions. So the cations are deflected into the opposite direction to the anions, and this separation of charge sets up a large-scale electric field. So depending on the conductivity structure of the ocean and the solid earth, these fields drive electric currents, which in turn generates secondary magnetic fields. So let's talk about the governing equations. So motional induction is governed by the following equations. So the local current density J in the conductor moving with velocity u is given by equation 1, where conductivity has its usual symbol, and B main, which is quite an alien symbol, is the ambient main magnetic field, and the U cross B main term is the driver of the motionally induced electric currents. So the induced electric field E counteracts this driver, which is the U cross B, and results in actual current J, and this current J generates a magnetic field which is known as the B ocean and is given by equation 2. So combining equation 1 and 2 and rearranging them yields an equation for the induced electric field, which is given by equation 3. So while the irrotational part of this electric field is maintained by an induced charge, the rotational part is at the opposite side is induced by temporal variations of the ocean magnetic signal, which is given by equation 4. So taking the curl of equation 3 and combining with equation 4 gives the motional induction equation, which is given by equation 5. And this equation 5 is valid inside the oceans and the solid Earth. So the fields above the surface are then determined by Laplace's equation, which is given by this relation for scalar potential of V of the magnetic field in the current-free region outside the Earth's sphere. So electric fields of motional induction. So already in 1832, Faraday had predicted a motionally induced electric field for River Thames, but he failed to detect it, and that's due to lack of adequate instrumentation as at that time. So such fields were then observed in 1851 by Wollaston in a telegraphic cable across the English Channel, which is the busiest shipping area in the world. So in 1920, Young demonstrated recording of the electric fields in the ocean by a ship towed electrodes. So submarine cables and towed electrodes are still the principal methods of measuring ocean flow by electromagnetic methods. So let's talk about magnetic fields of motional induction. So motionally induced magnetic fields can be divided into two. We have one, the toroidal, and two, we have the poloidal parts. So the toroidal magnetic field is generated by electric currents closing in vertical planes and is estimated to reach about 100 nanotesla in amplitude. It is confined to the oceans and solid Earth, and it can therefore only be observable by subsurface measurements. So for example, by ship-towed ocean bottom magnetometers. So in 2001, Lilly and Co. showed that magnetometer lowered by a cable from a ship can be used to determine vertical profiles of the ocean velocity. So the much weaker poloidal field with amplitudes up to about 10 nanotesla results from electric current closing horizontally, and it has a significant vertical component and reaches remote land in satellite locations. So induction by time-varying magnetic fields. So external magnetic fields generated in the ionosphere and magnetosphere vary strongly in time, exhibiting regular daily variations and occasional strong magnetic storms, which is caused by coronal mass ejections from the sun. So these time-varying magnetic fields induce electric fields and currents in the ocean, generating secondary induced magnetic fields. So the governing equations are a time-varying magnetic field induces an electric field E in the ocean, which is given by equation 6. So B is the sum of the inducing secondary and secondary induced magnetic field, and the induced electric field drives the electric current, which is given by equation 7. So generating a secondary induced magnetic field, which is also given by equation 8. So combining equation 6, 7 and 8 above, it shows equation 9, and the equation 9 is the equation for induction by time-varying magnetic fields inside the ocean. So in contrast to the motional induction discussed above, the oceans are assumed here to be stationary in the Earth fixed reference frame. So the field in the source-free region above the Earth's surface and below the external current systems is again given by Laplace's equation. So we talk about skin depth, which is also known as depth of penetration. So low frequency electromagnetic waves penetrate deeper into an electrical conductor than high frequency waves. So for a periodic external field with frequency V, equation 9 demands that the amplitude in a uniform conductor decays exponentially with depth. So skin depth is the depth at which the amplitude is reduced to 1e, and it is given by the equation down here. So where the frequency V is given in hertz, and a seawater conductivity of 3.5 Siemens per meter is assumed. So to effectively penetrate through a seawater column of 5 kilometers, magnetic disturbances have to have periods longer than about 6 minutes. But however, even up to periods of several days, induced fields are strongly influenced by the highly conducting oceans. So ocean induction by magnetic storms. So while daily variations during solar quiet conditions generate significant induction in the ocean, a much stronger effect is caused by magnetic storms. So strong magnetic storms generate ocean-induced magnetic force reaching magnitudes of more than 100 nanotesla. An overview of induction in the oceans by solar quiet and storm time fields is given by Feinberg. So the induced currents are concentrated near the coast and the horizontal boundaries of the conductor. So their magnetic signal is known as the coast effect. That's the coast effect of induced currents. The ocean-induced fields can be predicted for a given external storm signature using a 3D conductivity model of the ocean. Yeah, sure. So the induction equation 9, which has been shown previously, is solved either directly in the time domain or separately for all contributing frequencies with a subsequent inverse Fourier transform to the time domain. So in conclusion, we talk about the application of our topic in our country, Ghana. So in Ghana, the topic under study is applied in so many ways, but then we decided to talk about only two. So it is applied in underwater communication by the Navy, by the Maritime Corps and Coast Guards, and it's also used in the detection of submerged objects such as submarines and mines. So this is the end of our presentation. Thank you.